have a Stillman marathon, and Mike is not going to perform solo.
Okay, yeah. You'll be good and sick of me by the end. Okay, but at any rate, so today, in these two lectures, the first one, we're going to actually sort of go through the theorems of how to compute cohomology. But before that, I have to say something about sheaves and what we want to do with them. But even before that, I want to do something that was more algebraic in nature from last time. But it's actually good to do it this time because it's more relevant to what we're doing today. So, oh yeah, I forgot about this one. Now it's even tilted more. Oh, excellent. Okay. And now let's see. Where do I? Yeah. Oh, there's something underneath there. Yeah, that's okay. Now let's see. Is it okay? How do I focus it? Is that good? Okay. Good. Okay, so another algebraic thing that we need, and that's used a lot in this, are X modules. These are quite easy to compute, given that we know how to do free resolutions. So I'm just going to talk about the first one, just for now, xi of m into the ring S. You can also make this more general by doing into another module n. And actually, one of the things we are doing that might be useful for. But right now, let's just stick to the case of xi of m into S itself. So the steps are pretty simple. You take a free resolution of m out to as far as you need to go. In this case, let's go all the way to f sub r, because we know by the Hilbert-Syzygy theorem that this is finite. And so we have this. Then, as this sort of general homological algebra rubric, we just apply hom of S into S to the whole thing except for the m on the end. And that's all that is taking the transpose of this complex. So we just flip all the arrows around and make transposes. And then all we have to do is last time, especially if you did the exercise, you just take the kernel of the one f modulo the image of the other, and that module is just the x module. Okay. So today, the first half of today, or the second half, third of the day, whatever. So for this part, the main example is going to just be a fairly simple one, the rational quartic curve. We'll do a little more interesting examples next in the afternoon. Okay, let's see. Is that in focus? So I just want to talk about this one. This is a good example because it's a little less trivial than the twisted cubic, but still you can pretty much write things on the board or on the screen. And so what we have here is we have a parametrized curve from P1 into P3, which is just the map ST goes to all quartics in S and T, except we leave out one, S squared T squared. And we call these new coordinates A, B, C, D, and let X be the image of this thing. And the ideal, if you calculate what it is, either using the Gribner basis technology or just by looking at it and trying to figure out what it is, you see that it's generated by 4 binomial equations. They're one quadric, BC minus AD, and then 3 cubic equations. Okay? C cubed minus BD squared, and so on. Now, the minimal resolution of this looks like the following. So S mod to S mod I, the generators of Ix are there. It's a 4 by 1 matrix of F1 through F4, which I didn't rewrite. Graded wise, it's S of minus 2, because there's one quadric, and direct sum S of minus 3 cubed. Remember, the S of minus something or other is the same thing as S with the generator in degree 2 or 3. Now, if we calculate the syzygies on that by using the Grosvenor basis computation, you find this time that there are 4 syzygies, or rather, every syzygy can be written as a combination of these 4 columns. Minus b squared ca0, and so on. Okay. Now, and then finally we have this last one, d minus c minus ba. And I didn't actually write the slide that actually transposes this, so you have to do that in your head. This one will just be s of 4 to s. Actually, I should write this down. Where is it? Let's leave it. So when we transpose it, what's going to happen? This last map here will be a map of s to the 4 to s. What happens to degrees when you transpose? So when you take hom of this into s, it respects gradings. So now, I really need to write something down here. So the last map is going to be, and I will write it down in a second, is going to be s of 4 to the 4 to s of 5. And given by d minus c minus b and a. So it switches the degrees around. So it's now an s of 4 instead of an s of minus 4. Okay? So that's now the kernel, the X modules are going to be calculated here, 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 or here. And actually, let's do that by computer. Since my slide is a little weak. Okay, I'm going to get rid of this for the moment. So let's see here. Can you see it yet? No. Okay, so I'm taking Q of A through D. I'm taking the polynomial ring S and T. I'm just going to have it compute the ideal, just like Bernd did this morning. I'm going to take the map from S to P1, which is now given by these 4 quartic polynomials in S and T. And that's my ring map. The kernel of that, I, will be the ideal of the rational quartic. And there's the 4 generators. Okay, here's the resolution of this thing. It's S1 to S4 to S4 to S1, which is what we had over there. We can actually take a... we don't need to do that. We can actually look at the maps in it. This is exactly where I got those. When I wrote those down, I got it from this. So they better be exactly the same. Okay? So you look at a chain complex and you get the first term, the second, and so on. Okay? Now let's do this by hand. So that was C.dd. So I want to take the, let's see here. I want to do these X modules. So what I want is C.dd underscore 3. That's this map that that I had just written down right at the moment. And I want to take the transpose of that. Now notice it's now, there's a minus 5 there, which tells you the degree of what it's going to. That was the S of 5. And it's this. So we can now take the kernel of this, kernel of OO. It gives us six generators. These are actually, if you're familiar with it, these are the Kazul syzygies on those 4 linear polynomials that we had before. They were A, B, C, D with signs and permuted around. Now what we need is we need this one, C.dd. Oh yeah, which one am I computing here? Let's look at C again. So I calculated the kernel of the transpose. We can actually transpose this. Dual of that. Okay, so we have S1 to S4 to S4 to S1. We can look at all of these things now. And so here are the maps. So the first one up there, and that's, so we want to calculate the kernel of the images. Okay? So let's actually just do this. Kernel of C of this thing here, the transpose of C dot dd underscore 2 modulo the image of the transpose of C dot dd underscore 1. Okay? And this gives you what's called the subquotient module. And if I prune that, I get 0. I'm sorry I'm messing this up a little bit, because this is actually x1 of s to the 1 mod I, comma s is 0. Now if we want to do the next one up, we go back here, and we're going to change this, this to the third one, and then we take the image of the second one. Okay? And again, we get a subquotient. There's those 6 generators, the Kazul syzygies that we had before, modulo the image, which are these 4 guys, the 4 columns here. And so that's whatever that module is. We prune it to find out what it looks like as a co-kernel. And we get 3 generators. They're all in degree -3. And then modulo this, these 5.
Can you explain what happens as you go from A18 to 19?
Right.
I think it's an important step.
Okay, so first of all, let's take a look at 018. This is, if you use Macaulay et al., you're going to see these sort of things. The subquotient, first of all, what that is it's the image of the first map, which is a submodule of R to the 4, of S to the 4, modulo these 4 guys here. So it's an I modulo J, basically. And when you go to this one here, what it does is it takes those 6 guys and finds the relations on them, but minimalizes it. So let's take a look here. Over here we have the last 3 columns, CD00, actually appears in the generator set as well. CD00. So it's not going to appear as a minimal generator. It's getting dropped to 0. Similarly, AB minus C minus D, although it itself doesn't appear there, it's the sum of 2 of those columns. And so that one also will knock out one of the generators here. And similarly, the 00AB will knock out the last generator over here. So we had 6 generators, but 3 of them are 0. And so we have 3 generators left. Okay? And we have 3 generators left, and then it calculates basically what the relations are on that using a syzygy computation, using that exercise that I gave you last time. So, and then this is the end product here. This is an interesting one. This is x2. 2 is the codimension of this thing. So if I do this, comma s, I get the same thing as I should. x2 of s to the 1 mod I, comma s. And that's going to be, we're going to talk about this later, but that's the canonical module of this thing. So it's possible to get your hands on canonical sheaves and things like that. So at any rate, so there's x1, x1 was 0, x2 was this canonical module. What about x3? Let's just calculate it. x3 of s to the 1 mod I into s is the co-kernel of the matrix ABCD. Well, that's actually not surprising. If you remember from, let's actually look at the C, at the whole thing again. Let's try to put it on. Here's the whole resolution. The very last step is going, let's actually, so what it is it's going to be the kernel of the map that starts at this S1 to 0, that's all of S1, modulo the image of the Dix map, which is the ideal ABCD inside of there. So it's really S modulo ABCD, which is just a one-dimensional vector space, K, in some degree. Okay? And that degree is 5. Or minus 5. We can figure it out. Actually, let's take a look at it. So we did that one already. So it's co-kernel. So that means that the generator is in degree minus 5, and you're modding out by ABCD, so there's nothing further after that. Okay, I kind of bobbled this up a little bit. So are there any questions on this? this example. We're going to be doing this, this a little bit more, but let me,
Could I ask a question?
yes.
When you're computing the initial free resolution, have you set it up so that you automatically get something minimal?
Yes. So the question is, if you start with something homogeneous, do you get a minimal free resolution when you do the res command? And the answer is yes. If the thing you started with was homogeneous. That's actually not so much harder to get either from a Grosvenor basis calculation. Yes?
What's the ext? Is that relating
What does X stand for? Why is it called X? It stands for extensions. So, X1 it classifies extensions between two modules, so, and so on. So these are sort of higher X. Yes?
Is that 0, 0, 2 next to battery a bad thing? It's been going down. It looks like it might be bad. It's good? Okay.
Oh yeah, no, I've got it plugged in here. Okay. So
I didn't want your computer to die, I'm sorry.
yeah, I've got some old batteries. They could be bad. Okay, so over here, let's take a look again. For the moment, I think we're going to be pretty much done with this one for the time being. Actually, one thing that we should probably have done first to just make sure that we have everything right is do codimension, degree is 4, and the genus of this thing, it should be rational, so it should be genus 0. And, okay, so I'm going to turn this off if there's no other questions on that. And so meanwhile, here's what we had done. Whoops, where is it? It was right there. Ah, here it is. So we have this, here was the resolution, and then we had calculated the kernel of various, the transposes mod the image of various ones. X2 was the canonical module generated by 3 elements. X3, which is the one calculated at the very end, was S of this twisted by 5, which is the generated in degree minus 5. And at 0 elsewhere. And then any higher x is 0, and actually we saw the x1 was 0 as well. This is actually an important point of these things. So which x are non-zero? Whoops. Okay, so suppose we have a module M. You can think of it as S modulo I if you want, like the idea we just had. We have the codimension of that in S. So in this case, we had codimension 2. And we also have the projective dimension of M over S, which was in this case 3. So we're calling it D here. It's always the case that the codimension is less than or equal to the projective dimension. And here's the situation that you have with these X modules. The very first one, XC, is actually the very first one which is non-zero. In fact, that's one definition of the codimension. And then you have XC plus 1, who knows, it could be anything, up to XD minus 1. And then finally, X of the very last one has to be non-zero too, because it's the image of 0, which is something modulo something which isn't going to cover the whole thing. So, so we have this XD is not equal to 0. So this is sort of the picture of all of these X modules and what happens. And they actually have quite a lot of information in them. The very first one there is going to be the canonical module. That's actually got essentially similar information as to what you start with, almost identical. These other things are oftentimes for nice varieties, or for nice M equals S mod I, are going to be nice finite dimensional vector spaces over K. But they don't have to be. They could be much worse. And then this last one, well, or they're going to be 0. And then this last one will also be finite dimensional, oftentimes, but it doesn't have to be.
I'm sorry, I think you said it. Codimension meant codimension of the support?
Codimension of the support. So, so codimension of S mod I is the codimension of the ideal. By the way, in case you haven't seen this, the M is called Cohen-Macaulay, but there's only one of these guys that are non-zero, the XC. So that's the same, the codimension is equal to the projective dimension. And I like this definition of it the best. And it also is going to make the cohomology for Cohen-Macaulay things nice. Some might call this arithmetically Cohen-Macaulay. as opposed to locally Cohen-Macaulay. Okay, let's leave that there. Okay, so that's the example of X. So these are going to play a prominent role, and we'll get back to them in a bit. But for the moment, it's going to be, basically we have to do sort of a little bit of algebraic geometry class. Not much, but a little bit. The basic question is, what's the best way to define a sheaf? Okay? So I'm going to try to make this sort of reasonable so hopefully, if you don't know too much about sheaves, that's, you'll get something. And if you know a lot about it, then maybe it won't be too bad either. So here is the one way of defining a sheaf. So you take a basis for your topology. In our case, it's going to be the Zariski topology. So this is just a set of open sets that basically you can always find open sets inside of the ones you're interested in. And for instance, for the Zariski topology, the sets are the use of f, where f is any homogeneous polynomial, and we look at the set of x where where f is non-zero. So this is an open affine set, and these form a basis for the Zariski topology. Now, to specify a sheaf on X, let's call the sheaf F. Okay, to specify a sheaf, you have to give certain pieces of information. This is a slightly different. If you read Hartshorne, he gives all this sort of concocted way of getting it for every open set. But in fact, if you just restrict to these nice open sets, the use of F's, everything is just sort of a lot easier. So you have to give yourself a set F of UF. Well, it depends on whether you're doing sheaves of abelian groups, rings, but that has to either be an abelian group or a ring or whatever it is that you're making a sheaf of. So for every polynomial F, you have to give one of these things. Or actually, in general, any element of your base. And if you have an inclusion of two of these sets, you have to give yourself a restriction map. Now, I'm not going to go over the definition of what a sheaf really is, but these have to then satisfy the usual sheaf axioms. In particular, it better be the case that restrictions from one set to another is the same as going all the way. It better be the case that if I have a section which is on an open cover of it is 0 when you map it down, that it itself is 0. And similarly, if I have a bunch of sections that all map to the lower things, in other words, you can glue them, you should be able to find a section that it comes from. So this is sheaves in a nutshell, blown away, and which are probably completely useless. I've never seen it before. But in any case, so that's that. Okay, so we're not interested in general sheaves, though. We're interested in coherent sheaves. Now, as I think I mentioned before, they're going to come from modules. So if you don't like this way of doing it, you can just think of modules. But nonetheless, here is the way of doing it using this situation. Let's start with X is some subvariety of Pn. We could do this maybe more generally, but let's just keep our situation. X is a projective variety or scheme. And M is a finitely generated graded S mod I module. S mod I is the ring of X. Okay, a homogeneous ring. And now we're going to define, given that finitely generated module, we're going to define a sheaf on X called M tilde. And it's pretty easy. You do the only thing that you can do, given this setup that we've got before. M tilde, you have to give it on the open sets, use of F. And what you do is you invert F. Well, F is never 0, so it's sort of the natural thing to do. So I tensor over S with S of 1 over F. It's the same thing as tensoring over S mod I, since M is supported there, but it doesn't really matter. But we don't just do that, we take the degree 0 part of that. Okay? And then the map, UFG here, is just the standard natural map. If you invert by F and then you invert by F times G, there's just a natural. Now here's our definition of coherent sheaf. So you can define these in any number of ways, but for the purpose of this is probably the easiest. A coherent sheaf on X is just the sheaf of this form. Okay, these are it, okay? M tildes. And so you can think of it instead of, if you don't want to worry, if you're, depending on how comfortable you are with sheaves. There's two types of people in the world. Those comfortable with sheaves and those not quite comfortable yet with sheaves. Or maybe never comfortable. But in any case, you can think of it either way you want. In particular, it's your choice. You can either think of coherent sheaves or graded modules. Okay, now I want to give a few just basic examples, still in our algebraic geometry classroom here. Or whatever. Okay, so anyway, so O of x. So if I take a ring R, which is S mod I, that's a perfectly good S module, graded. I can take its tilde, and that's usually called O of x, which is the structure sheaf of x. Okay. Similarly, I can take, remember we have this operation of twisting, of changing the degrees by going from R to R of D, or M to M of D. We can do the same thing here, and we get OX of D. Is the way of saying that. The next one is actually very crucial. This is what is going to really allow us to do divisors and line bundles, and so this whole sort of geometry in terms of sheaves. Suppose I have a codimension 1 subvariety of x, irreducible. It doesn't have to be, but say it's irreducible. It's a nice thing. So if x is a curve, d will just be a point. And suppose it has ideal j, which we think of as being an S mod I module. Okay? It's an ideal inside of there. Then if we take the j tilde, we get OX of minus d, is the name for it. So this is one of the standard, this is the way of linking these kind of sheaves with divisors. And we'll see a lot more about this, not this afternoon, but tomorrow. Another example, which in fact I didn't actually show how to compute like I sort of had promised yesterday, and we might get to it if we have time, is the normal bundle that we had for when we were doing the Hilbert schemes. So here, the module was hom of I into S mod I over S, or it doesn't really matter what it's over. That module is a nice graded S module, and it's actually an S mod I module if you think about it, and I can take its tilde, its corresponding sheaf, and that's my normal sheaf, or normal bundle, often called. Any questions about this so far? It's if you've already seen it, I'm sorry about going through it, but if you haven't seen it, then the rest would be pretty much incomprehensible without it. So. Now, there's actually two things going on here. How good is this operation? M tilde, okay, great. I said we can think of it in terms of modules or sheaves, but that's actually not quite correct. The trouble is that it's not a unique operation. I can have several modules whose little twiddle sheaf is the same thing. And so we have two different operations going on here. Well, to M tilde, that's the one we just spent a few minutes defining. Okay? Our nice sheaf. But we have another operation, which I haven't really talked about yet. But if I start with the sheaf F, H0 of F, even though we haven't defined it, I think of it as the global sections of that. Just the value of that on X. So H0 lower star of F, though, is the direct sum of all these H0s. Turns out that is an S module, or an S mod I module, if you're doing it over X. Okay? And it's a graded one. You see the grading right there. So this is so going from a sheaf, I can get a graded module over the ring. And the question is, you hope that the situation is that these are inverses of each other, and everything would be nice. And that's sort of true. Oops. I am missing slides. Oh yeah, there's more on this one. Oh yeah, right. Whew. That's an important one. I didn't want to have to sort of go through and try to write that on. Okay, so here are a sort of a compendium of basic facts about this relationship. The first one is, suppose I do this M tilde. Well, you can get the zero sheaf sometimes. How do you get the zero sheaf? If your module M sub D, if you're in your module in high enough degrees, you're just 0. Okay? Then you're going to be 0. And if you look at the way that it was defined, this is just sort of almost immediate. On the other hand, one good aspect of this tilde operation is it's an exact functor. If I have an exact sequence of sheaves, an exact sequence of modules, for instance, a free resolution of it or something like this, and I apply the little tilde, I get also an exact sequence now of sheaves. And because of that, I can actually tell when two sheaves are actually isomorphic to each other. M tilde will be isomorphic to N tilde if for some D, I truncate my module. So M in greater than or equal to degree D means I just lop off all the stuff before that, and it's a module. And I do the same thing for N, and if for some D those two things are the same, then my sheaves are isomorphic to each other. This might be a little bit unsatisfactory as far as algorithms go, because I didn't tell you what you need to take for a D here. Okay, do you have to just keep going on, or what happens? As it turns out, you can figure out which D you would need to take, and we might see that later. Okay, and the final property that's important is this one here. Suppose I take my H0 lower star of F, and I take its tilde. Then there is no funny business. I get immediately my sheaf F again. Okay, so basically the only problem is that I have a lot of modules that can go to the same sheaf. But given a sheaf, I go back to a nice module. Okay. Well, nice is a little bit tricky, but we'll get to that in a few minutes. One thing I've sort of punted on a little bit here is the following issue. One thing I did was punted on the following issue. Okay, so here the question is, if I M tilde, I have two ways. If it's an S mod I module, it's also an S module, and I could do the M tilde on either X or on projective space. And the question is, what happens? I mean, one's a sheaf on one place, one's a sheaf on the other. What's the difference? Well, the answer is, it doesn't really matter a whole lot. And the reason is, once I see how to compute cohomology, it's going to be the same on both sides. So the HI calculated on Pn will be the same as HI of M tilde calculated on X. And we'll sort of generally bag the issue of where it is by just writing HI of M tilde, or something like this. Okay?
Excuse me.
Yes?
But computationally, can you actually use one or the other? I mean, can one give an advantage?
That's a good question. So the question is, computationally, will it make a difference which you do? And basically, the short answer is that the techniques we're going to talk about today are going to always do it over Pn.
Right.
But there are ways of doing it over the other one. And a lot of times it doesn't give you better ways. But for some things like vector bundles, it can actually help out. Okay, so now here's the situation, okay? We have our X as before. We have our ideal is contained in S as before. We have our module M graded R module as before. And F is now M tilde, is a coherent sheaf. And the question is, we're talking about computing cohomology. What do we really mean by that? Okay, that's the first thing to get off our chest right off the bat. Right off the bat, halfway through the second lecture. So here, what we have is the following. Oftentimes, what you really want is just the number, right? The dimension of HI of F, which is little hi of F. Other times you might want a description of it as in some natural way as a vector space. For instance, as rational functions or something like this. The other way is related to what we were just talking about as far as H0 lower star. You might be interested in the actual module structure, Hi lower star of F, which is, again, you take all twists of your M tilde, and you take the Hi of that, which we will define and see how to compute. That gives you a graded R module, and you might want that thing. Okay? There's one thing about this that actually I don't think I said there. There's one little itty-bitty problem with these modules. They're not finitely generated. Okay? So generally speaking, if you're doing things by computer, you want finite generation. But here, what happens? These things can be zero in all degrees, non-zero in all negative degrees, which means that they'll never be finitely generated. So what you might want instead of this, you might also want to be able to compute, I'll write it up here, Hi lower star of M tilde, or F, whatever it's called. No, I have it down there. Oops. You might want the truncation. It's interesting, you can't see that. Anyway, so here you have this Hi of F greater than or equal to E. That thing will be finitely generated for any degree E that you want to lop it off at. Yes?
I have a question. Wouldn't it be notationally better to replace the star by the gradient?
Yes, it would be.
Because it looks like a degree grading. Right?
That's right. And in fact, actually, if you try to compute it in Macaulay 2, that's what you would. And in fact, that's what I should have put here. Okay. Now what we're going to do is we're actually going to go through and get the theorems down for how to compute these things, pretty much. But first, we have to start with the definition of this thing. Right. Perhaps you've seen this the check complex. So suppose I have an open affine cover of my X, or projective space. That would be fine as well. And what I'm going to do is for every subset of, I have M of them, U0 through UM. M might be different from the projective space that I'm in. This is actually more general than all of that. Anyway, so suppose for any subset lambda from 0 to M, I let U sub lambda be the intersection of all those. And then I can define the check complex in the following way. I take C upper P of F to be the direct sum over all of these that's F of U lambda. Okay, that's F of U lambda where the lambda has size P plus 1. Okay? And then there's a natural way of getting a map. If you just sit down and think about it, there's really not too much options for what it is. And here it is written down. It's also written down in the lecture notes. Okay? So it goes from CP to CP plus 1. Now, then we let C of F be the actual complex here, going from C0 all the way up to Cm. And we just define Hi of F to be the cohomology of that. Okay. And the main theorem is that this is independent of the open cover as long as it as long as it's an affine open cover. Okay. So, and this is what we want to compute. Okay, so now we're actually going to start. That's the sort of general algebraic geometry thing that you would read about in Hartshorne, section 2 or 3 or something like this, and of chapter 3. And we want to actually now restrict it to the case that we're interested in. So actually, we can define something very similar to the check complex for a module. So I take my module M. Okay, the finitely generated graded S module, and I take M tilde as my sheaf. I can actually define Cp of M to be the following, which is pretty similar to what that other thing is. It's the direct sum of M tensor S modulo where I invert by a bunch of the variables at x's. So I invert by all the x lambda I i's where that appears in lambda. Okay. And then I have the exact map CP of M. Notice, by the way, I'm doing one thing different from when we define M tilde. I'm not taking degree 0 part of this. This is just some large thing. Okay? I'm not dropping it in degree. And I can, again, in the same exact way as before, define the map from CP of M to CP plus 1 of M. And so we get this complex, Cm, from Cm up to Cn of M, where n is now where we're in projective space. Now, that was the one thing that's a little different here. So it's in projective space, so it goes up to Cn, where we're in Pn. Okay, I know that this is a lot of, whether you've seen it or not, just a lot of sort of complexes going through and so on, definitions and so on. But the thing is that this algebraic form actually you can really compute with and really see what's going on. The first proposition is to match the two. So and then we will never need the check complex for the sheaves anymore after that. And the way we do this is if you take hi of M tilde, that is hi of C of M, but where you restrict to the degree 0 part. And why is that? That's because that is the complex, okay? If I look at the check complex and write down what it is, that is the degree 0 part of that. And similarly, if I take the direct sum over all twists, that'll be I'll take the degree 1 part, the degree 2 part, and so on, and I'll get all of these hi of M tilde. Okay? So it's just, at this point, it's just all sort of, just sort of standard things. Are there any questions at this point? I know this is sort of like ripping through. There are going to be lots of examples of this sort of later, but I wanted to sort of pack all this stuff in one spot right at the moment. I don't know if that's a good idea or not, but anyway, that's what I decided to do. Yes?
So if we replace projective space by something similar, like product of like Toblerone, it would be okay, right?
That's right. So the reason I actually define this here, instead of just doing it straight away on projective space, is that if we were doing it, there is other instances where this is useful. One of them is on products of projective spaces, which is the Toblerone. Or another case are toric varieties using one, but I'm not going to talk about that at all. But basically, you can do the same sort of thing.
Please make a third line on the left slide.
That, like that. So it's basically the CP of M is just this thing, which if you think about it, is just the direct sum over all D's of the value of the sheaf M tilde on that particular open set that you had.
So how does computation with this complex compare to this free resolution?
How does it work with the free resolution?
How does it compare to free resolution?
Yeah, we'll get to that.
Oh, you're right.
Okay, so we'll see how we'll sort of see how they're related. I'm not going to prove a huge number of things, but I'm going to try to give you the few words that if I were to put you into a room with no food or water, you might still be able to prove the result in time. So at any rate, so this thing here is, and let's see. By the way, this thing here, the fact that we have the hi lower star of M tilde is actually equal to this hi of the complex corresponding to the module, could actually be used to define the module structure on that. Notice I just sort of punted on that earlier. There is just a bunch of vector spaces, but there's some structure of S module or S mod I module, and that's coming from that. Okay, so that's that. Now, one of the things that Sarah did, he computed this then. You might as well try M equal to S. It's not very hard. And here's the result, which you'll find in most places that will do this, or they're stated in some form or another. Okay, so the cohomology of OPN is S tilde is the following. For I equals 0, it's just the ring S itself. Okay? If I is between 1 and n minus 1 inclusive, there's no cohomology, 0. And I equals n is an interesting one. It's basically the polynomial ring on the other on the inverses of the variables multiplied by 1 over x0 to xn. How do you prove this? Well, you say it's a good exercise. It sends its way out, but really what it is the following. You use the following fact. You use the fact that if I take this C of S, let me actually put that down again. So here's the C of S that we had. Okay, so, whoops. So here's the complex, think of it as M is S there, and everything here is just S with monomials. It's completely monomial land. So in fact, it has a z to the n plus 1 grading given by all the different n plus 1 variables. So once you realize that, you say, of course, well, what is it in each degree? If I choose a multi-degree, what does the complex come out to be? So I choose an m inside of z to the n plus 1. It'll have some set of 0, some set of negative values, and some set of positive values. And the exact exercise is, what is it? And the point is, it's recognizable as some complex that you've seen coming from simplicial complexes or algebraic topology or something like this, and you can just, boom, you've got the answer. And you can see exactly, it will turn out to be exactly okay, so that's a rough, that's called a hand-waving sort of deal. But this thing here is actually very important. This 1 over x0 to xn, k of x0 inverse, and so on. There's another way of writing that down, which turns out to be very useful. That's often, yeesh, it is. Okay. Let's see, how am I doing here? Oh, actually, I'm not doing too bad. Maybe I'm not doing too bad because I'm rushing through it too fast. But anyway, let's see how it goes, okay? So suppose I take a graded S module. I want to, the so-called graded K-dual is a very similar module. Basically, I look at my module in every given degree, all the different degrees, and I take the K vector space dual of each one of those. They're just all finite dimensional vector spaces, and I just take their K dual. And then I piece them together by the D component. This M check is going to be a graded module, and in degree D, it's the M prime minus D. So it's doing a peculiar thing. It's switching it around, and also it's so it's taking K dual and it's inverting the degrees. It sort of is the natural thing to do if you think about it. And actually, in this setting, what does that mean? It means that this thing over here, the x0 through xn is actually shifting. That's a degree n plus 1 monomial. So that's the s of minus n minus 1. And then this hn here, those inverses, is exactly this check of this thing here. Okay? So that's that. Any questions on this so far? 3 minutes. I'm about to state the main theorem on this. And then the whole point, okay, so now that once we have this main theorem down, the rest of the time, basically, we're going to use it and sort of do some things around it to try to figure out how it's actually useful with the examples. Here's the theorem that is also due to Serre. This one is a little different than, all the other stuff we've done would happen, like Bernd suggested, on Toblerones or other projects of projection spaces. This one is not quite so easy to state in language. So here it is. Let's, again, S is k of x0 to xn. And using X modules now, you can exactly zero in on these things. Hi lower star of m tilde. Remember what that is? That's the direct sum over all hi of m tilde with all twists d. Okay? You might only be interested in one of them, in which case you'll only be interested in 1 degree part of the other module here. And then you have to unwrap all this stuff I just said about checks and then twist of minus n minus 1 there to figure out exactly what that degree is, and that's done on the second log. Okay? So hi of m tilde is isomorphic to the vector space xn minus I of m into s, the dual vector space of degree minus n minus 1. And that actually turns out to be a really good way of doing it if you can calculate free resolutions of your modules m.
Say again, what's a good way of doing what if you can calculate? Could you repeat
If you can calculate a free resolution of m, then you might have a chance of calculating the x module. Remember, to calculate the x module, you started with an m, and then you took a free resolution of it,
Right.
and then you took transposes and took kernel mod image.
Right.
That can go bad on you any step of the way. Okay? In particular, it can go bad on you because the resolution might be too complicated in practice. But in principle, this is it. But it turns out that it's actually one of the better ways. H0, though, is a little sneaky this way. You don't get it on the... Actually, you didn't get this one on the nose either, the module structure. You have this nasty check, which is turning the module upside down on its head. And which is okay for a lot of things, but maybe not exactly what you want. We'll have to deal with that later. The second one here is how do we calculate H0 of m tilde? This is actually probably the most crucial one of all the ones to compute. And it turns out there's an exact sequence. Actually any element of m of, say, degree 0 will give you a global section of your sheaf m tilde. It's just the way that works. But there's a kernel to it, and there's a co-kernel to this thing. But they're very easy to represent. They're the last two x modules that you can see. xn here and xn plus 1. Okay? So basically, it will allow us, nonetheless, to say a large amount about the cohomology of these things. And we'll also have another way of doing it. So what we're going to do this afternoon is we'll talk about, well, we have a couple things, but one of them will be doing differential forms and this Hodge diamond thing. That's going to be the example thing that we'll do. And then we'll also say more about this and hopefully make it all more palatable in the end. So sorry for the technical aspects of this, but anyway, there you have it.